Hello everyone. Today we are going to discuss about the topic time dependent and time independent Schrodinger wave equation. So before solving Schrodinger equation, we should understand the background of Schrodinger equation, how this Schrodinger equation is developed. As we know that quantum mechanics was established with hypothesis given by de Broglie, and all the material particle in motion possess wave characteristic. It was developed with mathematical derivation given by Schrodinger wave equation in 1925. Schrodinger equation is developed using differential equation. Now, using electromagnetic wave equation, which was derived by Maxwell equation, we have del square E upon del R square minus 1 upon C square del square E upon del T square is equal to 0. We are well known with this equation. Now let's apply this for the material wave. So let psi of RT, wave function for de Broglie's wave at any time t. So for this wave function psi of RT, equation 1 can be written as del square psi RT upon del R square is equal to 1 upon mu square del square psi RT upon del T square. So this is equation number 2, which is the basis of Schrodinger equation, and here mu is the wave velocity of particle wave. Now as we know that this equation 2 is a second order differential equation, and every differential equation have some general solution. So the general solution for above equation is psi of RT is equal to A exponential minus I omega t minus kt. Now what we have to do, we just have to write this wave equation in different formats. So come to equation number 3. What we did here, we have just multiplied h cross square in the bracket term. So we get, and we can see the equation is psi of RT is equal to A exponential minus I upon h cross omega t minus h cross k r. Now in this equation number 3, h cross omega is nothing but energy that we already discussed in the previous lecture. H cross k is momentum. This is also discussed in the previous lecture. So the new form equation is psi of RT is equal to A exponential minus I upon h cross Et minus P dot R. This is equation number 4. Now here P is momentum, and it can be represented in the form I Px plus J Py plus K Pz, and R can be represented as Ix plus Jy plus Kz. Now what we are going to do, we are going to take the dot product of P and R in equation number 4. So you will get equation number 5, which is in 3-dimensional case, or we can say this is the wave function for 3-dimensional case. Now if we want the wave function for 1-dimensional case, so in that case the equation 5 can be written as psi of xt. The psi of RT is replaced by psi of xt, A exponential of minus I upon h cross Et minus Px dot x. This is the wave function for 1 dimension. Now please observe equation number 6. We are going to separate the x part and the t part. So in this case, what we did, I have highlighted A and exponential of I upon h cross Px dot x. This part can be represented as psi of x. So the new equation form is psi of xt is equal to psi of x exponential minus I upon h cross Et. Here psi of x is nothing but amplitude of the particle wave. So this is the basic thing we should understand before solving the Schrodinger equation. Now let's move to the Schrodinger equation. So we are going to start with Schrodinger time dependent equation. It means time dependent Schrodinger wave equation. Now to solve this, firstly we have to consider the situation of the particle, or we have to provide the data for the particle. So let's consider particle of mass m moving along x direction in conservative force field. Okay, next, potential energy, momentum and total energy of a particle is V px. Px, why px? Because we are taking a particle moving along x-axis, or one dimensional case we are going to consider, and E is the energy of the particle. Now in the previous slide we have already discussed about the wave function. So we are going to write it directly. So we are taking the wave function moving along x-axis. So it is psi of xt a exponential minus I upon h cross et minus px dot x. This is equation number 1. Now our objective is to find out the differential equation, Schrodinger's equation. So we are going to differentiate equation number 1 with respect to t. So after differentiating you will get the result. Now in this equation I have highlighted the part which is representing psi of xt. So putting this part as psi of xt, I'll get the equation as del psi of xt upon del t is equal to minus I upon h cross E psi of xt. Now again, rearranging this equation, I'll get equation number 2 as E psi of xt is equal to I upon h cross del psi of xt upon del t. Now observe it properly. On both sides, E is associated with psi of xt. On right side, I h cross del psi upon del t is operating on psi of xt. So according to rule of equality, E and I h cross del upon del t having same nature. It is operating or it is working on some function. So this E is indicating I h cross del upon del t, which is nothing but total energy operator. Now let's move to the next step. Now we are going to differentiate equation number 1 with respect to x, means with respect to position coordinate. In the previous case we differentiated with respect to the time coordinate. Now after differentiating, I'll get the result. Again I have highlighted some part which is nothing but psi of xt, and the new form of equation is del psi of xt upon del x is equal to I upon h cross px psi of xt. This is equation number 3. Again observe this equation properly. So we'll get px psi of xt. In the extreme right side you will get minus I upon h cross del psi of xt upon del x square. I have isolated some part on the right side. So it shows that this is again an operator which is operating on psi of xt, and this operator p of x, which is nothing but minus I h cross del upon del x. It is momentum operator in x direction. Now again we are going to differentiate this equation number 3 with respect to x. So I'll get the result. Now let's move to the next slide. So after solving, I'll get del square psi of xt upon del x square is equal to minus px square h cross square psi of xt. I am just going to rearrange this equation. After rearranging, I'll get equation number 4. Now we have to move to the energy conservation rule. So according to principle of conservation of energy in non-relativistic mechanics, total energy is equal to kinetic energy plus potential energy. Mathematically it can be written as total energy, that is capital E, is equal to kinetic energy In previous lecture we have discussed about this equation of kinetic energy, that is px square upon twice m, plus potential energy, that is V. Now what we are going to do, we are just going to multiply this equation number 5 with wave function psi of xt, and we will get equation number 6. So after getting equation number 6, please observe it properly. So after observing it, I can say I can get the value of E psi of xt from the previous value I have already solved. I can get the value of px square upon twice m psi of xt from equation number 4. Okay, so putting this value, I'll get equation number 7, and this is nothing but Schrodinger one-dimensional time dependent wave equation. If you observe the equation, this is a differential equation. This is second order differential equation. Okay, now if the situation is that particle is free, it means potential function V is equal to 0, or we can say potential energy is considered to be 0. So in that case, in equation number 7, we are going to put V is equal to 0, and the new form of equation is in equation number 8. This is also Schrodinger equation, but this is Schrodinger one-dimensional time-dependent wave equation for free particle. So here we completed with Schrodinger equation, okay, for one dimension. Now I have some discussion, or I have some note for you. What is this free particle and why we are taking V is equal to 0? So for free particle is a particle not bounded by any external force or in field free space. In quantum mechanics, it means region of constant potential taken as 0. So that's why we are taking V is equal to 0. Now again, let's talk about the three-dimensional. In previous equation, that is in equation number 8, what we did, or equation number 7 and equation number 8, this is a Schrodinger equation for one dimensional. If we want Schrodinger equation in 3 dimension, in that case what we will do, so we will just replace the term of one dimension with 3 dimensions, that is wave function will be converted into psi of rt. Here on the right side, the different second order differentiation will be converted into 3 dimension, that is del square, del x square plus del square, del y square plus del square, del z square. And what is this? This is nothing but Laplace operator. It is called as Laplace operator. Now using equation number 9 and equation number 10, we can rewrite this equation number 11, and this is nothing but Schrodinger 3-dimension time dependent wave equation. Now again, the case for free particle, as we know that for free particle V is equal to 0, so equation 11 can be modified as given in equation number 12. So this is Schrodinger 3-dimension time dependent wave equation for free particle. So here we have completed with Schrodinger equation in 3 dimension also. Now there is another form of Schrodinger equation. What that form is? Consider equation number 1. What we are 11. I'm very sorry. What we are going to do? We are going to just rearrange this equation number 11. How we are going to rearrange? Please check. So it is minus h cross square twice m del square plus v psi of rt is equal to I h cross del psi rt upon del t. Now if we observe both the sides, on both the sides a operator is there which is operating on psi of rt. On right hand side, the operator we already know, that is energy operator. On the left hand side, the operator minus h cross square upon twice m del square plus v, it is called as Hamiltonian operator capital H. So Using both the knowledge of both the operators, that is Hamiltonian operator and energy operator, we will get the new form of Schrodinger equation, which is given here, that is H psi is equal to E psi, which is nothing but Hamiltonian form of Schrodinger wave equation. So here we completed Schrodinger time dependent wave equation in three forms: one dimensional form, three dimensional form, and in the form of Hamiltonian operator. Now let's move to time independent Schrodinger wave equation. If you understand Schrodinger time dependent equation, it is very easy to understand Schrodinger time independent equation. First, the question should arise in your mind that why there is need of Schrodinger time independent equation. So, in some problem of quantum mechanics, potential of particle is not function of time. That is, it will vary with position only. What we can talk about this? That in some of the cases, the potential function V depend just upon the position coordinate, not on the time coordinate. In such cases, quantum mechanical behavior of particle is observed with help of time independent Schrodinger wave equation. Now let's start the derivation from here. Again, we have to consider the particle of mass m moving along x-axis. Okay, now here we have to replace the potential function v of rt with v of r. Consider momentum and total energy of the particle. It is p of x. Why p of x? Because it is moving in x along x-axis, and the energy is capital E. Now the selection of the wave function, it is very important part. Again, when you go to the first slide, you will observe that we have already solved this wave equation. Why we are taken this wave equation? Psi of xt is equal to psi of x exponential minus I upon h cross et, because in this equation we have separated both, that is x part and t part, that is position coordinate part and time part. So let's move to next step, that is we have to take help of time dependent equation to solve time independent equation. So we have time dependent equation in equation number 2. Now here I highlighted v of xt. Why so? Because we have to replace it by v of x. Now what we are going to do? We are going to differentiate equation number 1 with respect to time. So after differentiating equation number 1 with respect to time, I'll get equation number 3. Now use equation number 3 and equation number 1 in equation number 2. Means what we have to do? We have to replace wave function psi of xt with this wave function, and the from equation number 3 we have to put the value of d psi xt upon dt. So after replacing, we will get this equation. Now after rearranging, I'll get the equation as e psi xt exponential minus I upon h cross et is equal to minus I h cross twice m del square psi of x del x square plus v x psi of x exponential of minus I upon h cross et. Please observe this highlighted part on both sides, that is right side and left side. After rearranging, this part comes out to be common, and after cancellation I will get equation number 4. And just rearranging equation number 4, I will get equation number 5, and it is del square psi of x del x square plus twice m h cross square e minus v of x psi of x is equal to 0. This is nothing but Schrodinger one-dimensional time independent wave equation. Please observe equation number 5 properly. You will find that there is no time term in this equation. It is totally time independent. And also observe the potential function. Potential function is function of x only, not of t. Now moving forward. So for free particle, as we know that for free particle v of x is 0, so the equation will turn out to be del square psi of x del x square plus twice m upon h cross e psi of x is equal to 0. Now all this equation number 5 and equation number 6 is for one dimension. Now for 3 dimension, again that we did for the Schrodinger time independent equation. So we are going to replace with the Laplace operator and this equation, and after rearranging we will get equation number 7. This is Schrodinger three-dimensional time independent wave equation. Now this equation can also be written for free particle. Again replacing v of r is equal to 0, I'll get equation number 8, and this is Schrodinger three-dimensional time independent wave equation for free particle. So in this way we have completed both Schrodinger time independent and Schrodinger time dependent equation. Now what is the significance of this equation? Now at last, significance of this equation is that Schrodinger equation carry very important information about the matter wave which is moving with energy E and mass m, and position coordinates are x, y, z, okay, and the potential function v. Now observing this slide you can understand all this physical quantity have their significance. So here we can say psi is the wave function, E is representing energy, V is representing potential energy, Z is representing position. So this is the important information carrying equation. So in this way we have completed Schrodinger equation. Thank you.